Our guest for tonight is our own Isaac Cruz, and Isaac's very passionate in astrophotography. And he's more or less, I guess you would say, that we have other people that are very talented. He's pretty much our go-to man for this.
Okay.
And he's also the lead for the CAS imaging group here at CAS. And Isaac has work published in various magazines and books, and he is a citizen scientist with published research, exploration, work done on variable stars, eclipsing binaries, exoplanets, and lately extragalactic supernova research in cooperation with OSU through the Assassin program. And Isaac's presentation tonight will be the art and science of astrophotography. He's going to touch on the equipment that you need, some of the problems that you're going to run into, and he's also going to be touching on how we can actually make contributions to science through astrophotography, through astronomy. Okay? And without ado further, here's Isaac Cruz.
Thank you.
And Isaac's a past president. Past president. He's currently a trustee. And
As
he's
well.
the lead for CAS.
Thank you very much for such a nice introduction. Okay, so just like Brad actually did, I'm gonna put my CAS hat first, and CAS is the Columbus Astronomical Society Imaging SIG. So if you're interested on actually how to take images, how to use a camera, what equipment to actually buy, and how to actually take images of the cosmos, we have a group. We have a special interest group that actually get together and meet here in Perkins on the Saturday following this meeting. So next Saturday at 1 o'clock in the afternoon, I'll be here, and there will be some people here that will actually, also share the interest on how to take images of the sky. You're more than everyone is welcome to attend. It is for all kinds. If you're even just interested on actually taking pictures, please come. If you are a person that has a lot of experience and have been doing this for many years, please come over because I need help, right? I mean, on actually explaining how to actually do this. So again, next Saturday, 1 o'clock, Perkins, you're all invited. Okay? So I'll take my Cassie's hat and I'll put my hat for the presentation in here. Let me see if I can do this right. Ooh, yes. And yeah. So, good evening, everyone. My name is Isaac Cruz. And tonight we're going to be talking about the art and science of photography. And I'll be going back and forth because that's basically the way I have. And I have different things in here. I actually brought some things to talk about and some equipment that at the end of the meeting you can actually come over and you can actually see and look at, and we'll do a quick setup so you can see how to actually you can actually do this with modest equipment and to actually get you started. So tonight. We'll talk a little bit about the philosophy, or basically the things that actually inspired me for 20 years ago when I actually started doing imaging. We'll talk a little bit about the challenges of imaging, and there are many, and we'll talk about some of them. We'll talk about equipment and what can you use and so forth. Not extensively, because there's all kinds of equipment, but at least to get you started and give you an idea. We'll talk about an approach, what to do first, if you will. If you're interested, how to get started. I'll show you some of my pictures, and some of them were published and some of them not, but I'll tell you what equipment was used to actually take it, and also I'll tell you, basically what I did to be able to take, those images all together. And after that, we'll talk about science. As one of the things that is really amazing about astronomy is that it is one of the very few ways that regular Joe, I mean anyone, can actually make a significant contribution to science and to the body of knowledge of man. So we'll talk a little bit about that, and then we'll have a little bit of QA. So the appeal of astronomy, right, is both intellectual and aesthetic, right? Sorry. It combines the thrill of exploration and discovery. I'm just reading what it says in there. The fun of sightseeing and the sheer pleasure of first-hand acquaintance with incredible, wonderful, and beautiful things. But it also offers the privilege not to be taken lightly of adding something to the knowledge and understanding of man. Those are not my words. They're really kind of pretty. 20 years ago, I actually bought a collection of 3 books written by Robert Burnham Jr., one of the first and very best celestial handbooks. And by the way, if you can find these books, I would suggest that you buy them. They're really very good. Robert Burnham Jr. He was an astronomer from Arizona, and he actually compiled these 3 books, which basically everything that he could see scientifically, as far as numbers, where these things are, and very, very scientific details, but also has an incredible amount of prose. When I say that is that the way that it's written is actually readable. It's not like, it's not just basically something that you basically just kind of look for an object in the sky, and it tells you where it's at, and what time of the year it actually comes up, and so forth. But Robert Burnham actually wrote an amazing compendium of ideas in his handbooks. Okay, and these words are actually in the introduction of this book. Okay, and when I read that, it touched me. I mean, it really did. It basically kind of got me to be curious about what is out there, and also, in a sense, personally, I wanted to share the things that I actually learned, and that was something that it did touch me. Again, Robert Burnham Jr., The Celestial Handbook: An Observer's Guide to the Universe Beyond the Solar System. Excellent book. So, if you can find them, just get them. So, let's start with the items that the first things that you actually find when you're going to take some images, right? So it has some challenges. First of all, most of the equipment that we have in our homes and that we use to actually take pictures of, are designed to take pictures in light, right? I mean, so we actually have cameras, normal cameras and so forth, that are designed to actually take pictures, when there's plenty of light. All our objects are dark, right? I mean, we actually take images when there's no light, right? So light starvation, right? Things are, definitely, they're very dim, right? So that's all it means. There's also low signal to noise ratio. That means that they're very faint, and the amount of contrast between the background and the object itself is actually very, very low. So there's a reason why we actually call it faint fuzzies, right? They're faint, they're fuzzy. Another challenge that we actually have is just that when you take a picture of a celestial object, it's moving, right? Well, the Earth is moving, right? The object itself is not moving, but hey, the Earth goes around once every 24 hours, sidereal rate. So everything seems to be moving at that rate, 15 arc seconds every second. That's basically what that means, okay? So obviously, if you want to take an image of something, you have to follow that object to make sure that you can take a good image. And another thing, which is kind of, we'll get to focal length dependency. Another thing is we'll define what focal length is in the next slide. But basically, it has to do with how much magnification the equipment that you're using actually, provides. If it's very, very, very long focal length, you have a huge magnification. Everything. You may be able to see something, but everything is amplified by that amount. So any type of mechanical error, if you will, or if you touch the equipment, the telescope or the mount or whatever, it's amplified by that much, and that will ruin an image as well. So that's where the focal length dependency actually comes from. And then it's target size. I mean, these things are tiny. I mean, they're really small, okay? When we actually look at and take pictures, a big thing is the moon, right? And the moon, if you take your thumb and you put it, at arm's length, that is the width of the moon, right? I mean, that's half a degree. So that's, and almost everything else that we take a picture of is much smaller than that, okay? So also the target size, which means that we need amplification. We need magnification to be able to, see what we're trying to take pictures of. So basically, what we're going to be doing is we'll talk about telescopes, the types of telescopes, and what do they look like inside. We'll talk about cameras and the different types of cameras that can be used to take images altogether. We'll talk about mounts, right, where everything is mounted, and then we'll look at some imaging setups that you can actually use. Okay, so let's start with telescopes, right? So a refractor, right? Most of you are familiar with this, right? We have one in the back, right? I mean, this is the traditional telescope. Good old Galileo came up with this design. It's very kind of straightforward in design. You have an objective lens, which is this guy right here. Light comes and it passes through the objective lens, and the light is refracted or bent. That's a fancy word for bending the light, right? So the light is bent, and then down here, it actually converges in one point. And the distance between the objective lens and the focal plane is the focal length. Hey, not that hard, right? I mean, so that's actually pretty cool. So basically, that's the kind of the magic, when people talk about what's the focal length of your telescope, they talk about 660 millimeters, okay? Well, that's the distance between the objective lens and the focal plane, where everything comes into focus. We call it prime focus, where the point where everything comes into focus, that's the focal plane back here. So basically, these telescopes, that's what they have. The more expensive telescopes will have other lenses inside here that actually are used to ensure that some of the aberrations, some of the changes that the light that occur to the light when it goes through the objective lens are corrected, and then you actually have things like no color aberration. That's normally what usually happens on this. The more of those lenses that are inside of the telescope, the more expensive the telescope is. So pretty simple and quite popular. And one thing that you can actually see here, right, is that because the focal length is from here to here, right? Then at this point, the longer focal length you want, the longer the telescope is going to be. So just keep that in mind. All right. So the next one is the reflector, right? We had the refractor because it refracts light or bends light. So the next one is the reflector, and you folks probably have seen this too, right? These are quite popular. They're quite popular mainly because their construction is relatively simple construction. You have a mirror back here that actually reflects the light, reflector, get it? And then there is a secondary mirror that bends that light into a focal plane that is typically on the side. Have you ever heard the term Newtonian? So Isaac Newton came up with that, with a telescope, like that. And Dobsonian. You ever heard of a Dobsonian telescope? That's also a reflector. It's basically the same thing. You basically have incoming light. It goes through, is reflected by the primary mirror. It goes to this flat secondary mirror, and then you have the focal plane. So what is neat about this, right? I mean, what is neat about this is that you actually can get a relatively large mirror, and your focal length basically is shortened up a little bit because you actually have the light bouncing off the secondary mirror going to the focal plane. Most of these telescopes are, they can be rich fields. That means that their magnification is not huge, but they give you a very, very nice field of view for a relatively simple design altogether. So these are beautiful, excellent telescopes, and yes, you can actually image with through these telescopes as well. You would actually, again, remember the focal plane in here, so you can image with this as well. And then for something a little bit more complicated is the catadioptric type of design. And in this one, basically the trick in here is to follow the light, right? We have incoming light. It actually goes through this corrector lens first. So it goes in, the light is corrected a little bit, so basically every ray of light actually, I was going to say impinges or just touches, is reflected by this primary mirror, and then light goes to a secondary mirror in here, and then is reflected back into the focal plane, or where your camera is going to be located. The benefits of this is that the length of the path of light is quite large, right? I mean, basically lights come in, it's reflected, and it comes back out. So you can have a relatively long focal length in kind of a, in kind of a more or less small enclosure, right? And because the aperture of this thing actually can be quite large, let's say 8 inches, 9 and a quarter inches, 10 inches, 12 inches, and so forth. These are excellent for actually doing deep sky because they gather a lot of light. So they make a nice light bucket, if you will, for us to use. So there are, as far as other designs, this is a Schmidt-Cassegrain. So this is a Meade Celestron. This is Celestron. Meade basically makes exactly the same style. I have a corrected Dal-Kirkham. That is also a catadioptric. The interesting thing about this, the corrected Dal-Kirkham, the CDK, is that basically instead of having a corrector in the front, it has corrector lenses in the back, and then it goes to the focal plane. That's the only difference, but still, it uses the same optical design to give you a long focal length in a relatively modest size type of telescope. So there you go. And again, long focal length, very hard to actually start with. So just keep that, just keep that in mind. So the three things that we have, the three designs that we have talked about, this is what you can actually use to, to take pictures of the sky. So, what do you select, right? What do we start with? Okay, so first of all, one of the first things, if you come over to next Saturday and we talk about, hey, I want to start actually taking pictures, the first question that I'm going to ask you is, what do you want to take pictures of, right? The typical answer that we get is everything. Well, let's not go there, because let's start with something simple, right? I mean, and that's really the key. The key to actually have fun and enjoy this hobby, the astrophotography, is to do the CAS, the keep it simple type of methodology, if you will. So when you start, the first thing that I'll tell you is that one of the things that you may want to do is you start with a short focal length with a wide field of view. And the reason why we want to do that is because I'm going to introduce you to the concept of image scale, right? Image scale is how much of the sky you actually how much of the sky can your kind of pixel in your camera can actually see. That's the image scale. The larger the image scale, the easier it is. Remember, the easier it is to take images. Remember that I mentioned that everything in the sky is moving, right? So 15 arc-seconds per second. So if you have a pixel scale of 20 arc-seconds, hey, I mean, you can actually take a couple of second images, couple of second pictures, and that'll still be in 1 pixel. And if you don't care if the image actually just slides for 2 or 3 pixels, hey, all of a sudden you can take like a 10-second image, and you'll be none the wiser. It will look really, really nice, really, really nice picture. Okay, so this concept of image scale is kind of important, and as we learn what this becomes something that is important for us to kind of understand. So when you have short focal length, when you have short focal length,
I didn't get that. Could you try again?
No, I'm not going to try again. So when you have short focal length, you have large image scale, which makes things a lot simpler, right? So, and that's why I say there lessens the sensitivity to mount errors, okay? Because again, the mount is an electromechanical device that is there negating the movement of the Earth, right? It's rotating at sidereal rate, so everything should stay immovable, right? I mean, if everything was mechanically perfect, everything is nice and clean and smooth, you basically can take perfect pictures all the time, but that's not real life, right? Mechanical engineers here are part of this group, and they know that really things have small imperfections that will basically move the relative portion, the relative subject that we're taking a picture of, and it will ruin the image. So if you start with short focal length, this lessens the sensitivity of the mount errors, and you have a higher probability of success. So that's where you want to start. As you get better and better, then you can actually start thinking and using higher magnification or longer focal length telescopes. That again, it just means that you have a smaller image scale. And that means that the mount that you're going to be requiring to take good quality images and pictures that you'll be happy with, okay, is going to be a much more precise mount, that translates into money. So just remember that, okay? The higher magnification, much harder to image with, right? So that brings into the telescope selection. The cost of the telescope itself. We mentioned that if you have a single element type of refractor telescope, that's going to be much cheaper than when you actually have a multiple element refractor type of telescope. So higher quality glass demands a higher price. That also is the same thing with mirrors. And of course, the larger the aperture, right? If you like to really kind of get a big bucket, then that means that you're going to be spending a significant amount of dollars associated with that as well. For example, let's talk a little bit about catadioptrics, right? Large focal length. They're usually an average size, 9 to 10 inches for aperture. The thing is that for a Smith-Cassegrain, the mirror is a spherical mirror, and there's a Ritchie-Chrétien type design, and the mirror is a hyperbolic mirror, which of course is much harder to actually make than a spherical mirror. So if you want a Ritchie-Chrétien type of telescope, you end up paying for that labor of making that primary mirror, so it actually is a fine piece of optical equipment. So that is what normally happens with the equipment. All right, so let's go to the cameras, right? Cameras. Probably most of you, if not everyone, has a DSLR at home, right? If you don't, that's fine. That's no problem. The DSLRs, we have Canons, we have Nikons, we have Sonys. Those are, kind of three. I'm just throwing those out mainly because those are good cameras. They have great sensitivity to the light. They have a relatively low noise floor. So basically, that means that you can take, long images and not basically be super, super noisy, if you will. And they're very popular. That's what I mean. So, in fact, I have one right there, right? I mean, and that was just my regular camera, just the camera that I use to go and take pictures of birds. So there you go, a DSLR, regular DSLR. To use them in a telescope, you can use them either what you call prime focus. Remember I mentioned that before, which means that you take your camera and you put it on the back of the telescope with an adapter, of course, and the detector on the camera will be on the focus plane, and everything should be in focus in there at that point. Or you can actually use it. You can actually use, like things like a projection. Projection means that you have an eyepiece, and then whatever you see on the eyepiece, you can actually go ahead and take a picture with your camera. That nowadays, actually, that's a lot easier with telephones. As it happens, I've seen many, really kind of decent images that have been taken by folks by just, hey, that's let's say a 20 millimeter lens, eyepiece, and they just put their camera, which is about close to 20 millimeters, put it in there, kind of like press the button and take a good picture. That is projection, and again, you can do that with, regular digital cameras, even the phone. That's as I mentioned before. Now, as you get better and better, and more curious about what you can do with astrophotography, then you start thinking about, well, okay, I'm done with the DSLR. I have reached the limits, if you will, of my enjoyment by using a DSLR camera. DSLR is also called a one-shot color, right? Because you press the button and all the colors actually appear. You don't have anything, you don't have to basically fool around with things like filters and things like that, that if you get into a astronomical camera, then that's the thing that we actually start getting into. Astronomical cameras come in basically two flavors, CCD or CMOS. CCD is being used for the past 10, 12 years or so, maybe a little bit more. The new, it's not newfangled, but basically the new technology that actually is coming up and getting to be quite popular is the CMOS type of detector, right? So that describes just how the detector is actually made. But the important thing here is that in the old days, CCD were very, very, in fact, they're still very good cameras around that have a very, very good sensitivity. And, most of them are monochrome, even though there's some one-shot colors as well. But CMOS actually has developed to the point where the now CMOS have more or less about the same sensitivity, but the noise floor is really, really low. I mean, it's really quite amazing how the technology keeps on developing, and we're actually getting this new cameras that actually now take very, very clean images compared to what we used to have with CCDs before, right? So that doesn't mean that a CCD camera is bad. It's just that you basically have to do a little bit more work with darks and stuff like that than a CMOS a camera that you get to use today. Cameras, as I said, come in one-shot color, which is just like your DSLR, the same type of idea. You say take a picture, and internally you have basically three filters: the red, the green, and the blue, and then the electromechanics of the image itself are such that you end up with one color image. So all those colors are appear, if you will, on one image. The monochrome basically is quite interesting. Monochrome cameras are relatively more sensitive than the one-shot colors. So basically, what ends up happening in the long run is that you'll have two paths, right? I mean, you either stay with a one-shot color and you keep on taking pictures like that, or you basically go with a monochrome, and now you're taking deeper images, but now you have to use things like filters, a red, a green, and a blue filter to actually take, to take an image. So put them together, and now you have a color image again. That means more time, right? I mean, because you actually have to take, the picture at least 3 times to actually have those 3 colors, compared to what you would spend taking an image with a one-shot color. So, hey, there are some pros and cons that are associated with that. Great question to talk about if you come over next Saturday about the idiosyncrasies and things that actually are associated with the difference with with those cameras. SBIG is a old and true type of company, Santa Barbara Imaging Group, and the same thing, QSI, very good cameras. They're still around, and I don't think that they're CMOS QSI. I think that all of them are CCDs. Their development has quieted down as far as making new cameras. The new kids on the block are the ZWOs. Those are Chinese cameras. They're all CMOS cameras. Great bang for the buck, and excellent performance for for the price. QHYs are coming. Yeah. Right. So one thing is that these are actually used again. Deep sky are kind of like, this is kind of the equipment that you will use for deep sky. If you're interested in taking planetary images, though, then you can get a dedicated planetary camera, and they are relatively small as far as the size is concerned, because they have a very, very, very dense detector. And again, a planet, because it just looks tiny, right? I mean, the technical term is distends. It distends just a tiny, it just looks tiny when you actually look through it in the telescope. So the only thing it has to illuminate is a very small detector. So QHY actually has some beautiful, excellent cameras, excellent planetary cameras that kind of do extremely well. And the reason you say, well, what the heck is that? Well, put a webcam in here, because if you get a webcam, you don't do that anymore. But in the old days, when we didn't have dedicated planetary cameras, you could use a webcam and basically take a movie of the planet that you're actually taking a picture of, and then process it, and you'll end up with a relatively good planetary picture. So these can be used as planetary cameras, because they take movies. You basically turn it on, and they take either 30 frames per second, 60 frames per second, 120 frames per second, depending on the interface, how you connect it to your computer, and how much memory you have, and stuff like that. Kind of sundry details in there. But the important part in here is that they actually make some very good ones. Secondary use for this is guiders, and we'll talk a little bit about what a guiding camera is all about. But they are basically, a guiding camera just needs to have just needs to take a picture of one star. So the tiny detector in there is perfect for just taking a picture of one star. All right, so how do we do this, right? I mean, that's the next step. We have talked about projection through the eyepiece, right? That you can actually take some pictures like that, and you may be happy with the results. In fact, I've seen some very, very neat results taken through projections. I'll tell you what. If you come here for, like in the summer, when we actually have a celebration of the sun, you will see, you can take pictures with telephones on a solar telescope, and those, you end up with some really nice images. I mean, really, really, really good ones. So projection, definitely a way of taking an image. As I said before, with the modern telephones, the actual camera lens is about the same size of the diameter of the eyepiece. So you end up with a very nice pairing, I mean, of the camera and the eyepiece all together. It works for, as I said, bright objects like the sun, and also for planets. You can actually get it. Sometimes it usually takes a lot of work, but you can actually take some good pictures with that. We had a member that actually took a picture with his phone. His telescope was actually pointing in the direction of the Orion Nebula. The field of view was huge, and he got a picture of the Orion Nebula. He was like, "Oh my gosh, I took a picture of a nebula. Great, that's pretty good." For getting into astrophotography again, kind of seriously, all of a sudden, you'll need an adapter that you can put in your DSLR or the camera that will allow you to connect the frame of the camera to the telescope, and then at that point, that you'll be taking images in what is called prime focus. Again, the point where all the light becomes in focus. And basically at that point, the telescope is just your lens. That's all it is. Your telescope becomes your camera lens. It's a long camera lens, right? 660 millimeters, 3,000 millimeters, right? I mean, it's like a 3-meter, big, large telescope. But in that case, it's kind of a nice way to actually visualize. Okay, the only thing I've done is just I have replaced a regular, like 35 millimeter lens with a much larger and longer focal length lens. All right. So, again, because we talked about that everything else is moving, let's talk about mounts. All right. If there's anything that you remember from this lecture today, okay, the takeaway is this, okay? If you're going to pursue imaging, please get the best mount that you can afford, and there's a very, very big reason for that, okay? This hobby is definitely can be extremely frustrating, okay? If you start with a bad mount, I guarantee you that you will quit. Basically, you won't be able to take good pictures. You'll be frustrated. You'll have so much. It's just basically not a good deal. You'll save some. You'll think you'll save some money, but if you really want to take images and you're serious about taking images, get the best mount you can afford now. Okay, and when you come on Saturday, we'll talk about that, okay? It's okay. I mean, it's kind of doesn't, in the end, you end up saving money. Because what happens is, if you buy a bad mount, you end up realizing that it's a bad mount. You buy a second mount, which may not be the best mount that actually, you need to be able to take some pictures. And then finally, you end up buying the mount that you were supposed to have in the first place, and you have spent twice what you were supposed to be spending. So, again, the takeaway is get the best mount you can afford if you're going to pursue imaging, right? So, now that you've made that decision, and it's kind of a rational thing, what do you do, right? I mean, you need to actually put it somewhere. Well, a big important part of how the equipment is going to be, put together is that you have to ensure stability for that mount, right? Again, the mount cannot move. It's just basically you want it to follow things at sidereal rate, but nothing else needs to move. So you need a solid tripod. Meade giant tripods and the Meade regular tripod actually are fantastic tripods for any mount. I mean, they really are very good. There are some other ones, but I know Meade tripods are very popular and very easily obtained. And there's a couple of types of mounts that you should know about, right? One of them is the alt-az, goes for altitude and azimuth, and we'll talk about that. And then there is the equatorial mount. So let's start with the alt-az. So the alt-az just moves, right? This is the azimuth in here, so this actually rotates. And then this is the altitude. It has a little motor in there, and this thing can kind of go up and down. So, and that's really nice, because, I mean, that's really intuitive, right? I mean, if you wanted to, point that way, it does, right? I mean, you can move that way, and it goes up. And, I mean, that's exactly what it does. So it's really nice and very intuitive and so forth. I will caution you, though, that if you want to take images with an alt-az mount, basically yeah, you'll get an image, but as it follows the object, it basically rotates. It begins to rotate. So you need a derotator for effective imaging. The easiest way of actually not going through that is to actually get a wedge that you put between the mount and your pier or your tripod, and then that wedge converts this alt-as mount into an equatorial mount. Okay? An equatorial mount, also called a German equatorial, it's kind of neat because basically what it is that the one axis, this axis right here, right, is actually aligned with the celestial pole. And everything in the sky rotates around the celestial pole. So one axis, basically, once you have it there, hey, you don't have to worry about actually moving things around very much because everything rotates around it. The only thing that you have to worry about is to find the object itself. Now, again, if you're going to this manually, sometimes the equatorial mount is not intuitive on how to actually find things because things kind of move kind of funny because everything is aligned to the celestial pole. But if you connect this to a computer and you tell it go to M31, right? It'll do it, and you don't care how it moves. Basically, it'll find the object and basically will go. So other than the part of being kind of funny to actually find things, and you get used to it, the equatorial mount is kind of the easiest and most effective way of actually finding things and using this type for effective imaging altogether. The prices vary tremendously because you have good mounts and regular mounts, and then very good mounts and very good mounts. Okay, and it's up to you to actually spend the money, but just remember, buy the best mount that you can afford for the type of imaging that you're going to be doing. Okay, and I'll give you it's not a spoiler, but one of the things that we'll be talking about is what type of equipment you will need depending on what you want to take an image of. And I have handouts, so you don't have to go crazy at remembering everything. The handout actually will give you some idea of what to buy and what to get to be able to take some images if you're interested on altogether.
Isaac, maybe you should talk a little bit about an equatorial mount. Counterweights are actually very important in an equatorial, as opposed to an alt-as, which typically doesn't need counterweights because it's up and down.
Excellent.
Yeah.
That's very true. As you can see here, this equatorial mount has a counterweight in here, and the reason why that is important is because your telescope is here, but it basically pivots around this axis, right? I mean, the equatorial axis. So in order for the motors to be able to move the telescope effectively, right? I mean, without the motors actually, you need to balance the telescope with some counterweights. So basically, you're neutral, and at that point, very small motors actually can move a lot, right? And the movement again is at sidereal rate, so you're not moving really, really fast. But still, in order for you to be able to move, a big mass, then you need some counterweights to be able to do that. Thank you. That's excellent point.
One of the points about the versatility of mounting any scope on that, as opposed to the others.
Yes, an alt-as, if it's basically something that it's, something like a fork, you basically have, the size of your arms is what determines how large a telescope you can actually put in there, and so forth. So they usually come like as basically a kit, if you will, right? I mean, just come as one unit. The good thing about equatorials is that you can basically put any type of telescope that you want in there, refractors or reflectors and so forth. Usually, again, we talked a little bit about the prices. The higher the payload that a mount will actually handle, will also dictate part of the cost of what it has to do, right? If you have a mount that can handle 250 pounds, is a lot different than a mount that can handle 25 pounds, right? That's kind of obvious, but it does happen. Okay, or you can do your own. This is an equatorial. I put this in here. This is actually kind of an interesting, what is it? Something that we want to talk about, because basically this is an equatorial mount, right? This hinge right here is actually pointing to the celestial pole, right? You put your camera, here's with your lens with the ball and socket mount, okay? And then as you move this, you rotate once per minute, this surface in here begins to move, to rotate this way, and that counteracts the movement of the Earth, right? So there you go, right? I mean, what is moving? The top board. This board right here. Which way? It rotates around this hinge. So it's moving this way. So there's the hinge, and this moves this way. So, and that's because this is pointing to the celestial pole, then you're counteracting or you're following the objects as they move, as they rotate around the celestial pole. So there you go. I mean, and you can literally, and this is great for kids, I mean, as a project and so forth. Can anybody tell me which angle is this angle right here?
Depends on where you live.
Depending on where you live. That's right. It's a latitude. Yeah. For us, it would be like 40 degrees.
Yeah.
Because that's where we basically live. Yes.
Yeah, I've built those many times, and if you use a quarter 20 screw, it's 11.45 inches to the hinge. You can go about 10 minutes or so.
Yeah, exactly.
Around, 11.4, something like that.
If anybody wants the design specifications, just ask, because that actually again, this is kind of a neat project. School, and kids and stuff like that. It actually does work. Okay, I brought a commercial version of a barn door. I mean, I'll show you to you at the end of the presentation. I'll show you. I mean, it's this thing right here, but I'll show you how it works. It's kind of neat. This is the commercial version of a barn door. This thing right here. I'll show you all how that actually works when we're done with it. It's kind of a neat thing. All right. So this is kind of like where we actually put all this stuff together. Let's talk about what imaging setups actually are useful, right? So depending on what you're going to image, right? I mean, as we said before, the first question that you want to ask yourself is, after you get the best mount you can afford, is what type of object am I going to image, right? So if you're going to be imaging like planetary, stuff, okay, or do you want to do deep sky, or do you want to do some wide field imaging? And I want, this is a good thing to start with, right? I mean, just go ahead and again, it's part of that keep it simple type of mentality. Select one of the three, not all three, just one of the three to actually get started. And it's beeping. And then basically, this is the answer slide. And then match whatever you want to do. for example, okay? If you want to do planetary, you're going to basically need a long focal length type of telescope, okay? And you can use a refractor for a telescope, but it has to be, you need to be able to make it a long focal length somehow, whether you use some optics, to be able to double, triple, or even make it 4 times the focal length. Barlow's, I'm sorry, my head. Yeah. Yes, and long focal length, SCTs is the most common to actually take planetary images. And then, remember that planetary camera I was telling you about? You go ahead and use that camera. If you're interested in wide field, and this is what I recommend for you to start with, okay? Start with wide field. I mean, it's easy. I mean, it's relatively easy. You can use a short focal length type of telescope, and you can use a refractor. I mean, a short focal length refractor extremely well. You can use a regular lens, a regular camera lens. That's a short focal length, right? I mean, that's a short focal length refractor in there. And then you can use your camera, your DSLR. You can use a reflector as well. But in the case of, when I say reflector in here, you can use, Newtonians are actually great for short focal length, if you will. So this is where I suggest that you actually start. It gives you the most probability of success without too much trouble. And then once you're experienced and you actually know what you're doing and you're actually, kind of, if you want to graduate, if you will, try deep sky. Deep sky, long focal lengths. You can use, a reflector, typically. You can use refractors for this guy as well, but they're kind of tiny. So, for the most part, you can use a reflector very well. And then a CCD or CMOS camera, CCD or CMOS astronomical camera, again, will get you there. This slide, I have handouts. So if you're interested on it, I made enough copies for quite a few people, and if we run out, just let me know. I'll make some more. Okay. So this is the answer slide right here. So this is kind of the neat thing in there. All right. So let's say you want to start, right? So start with your low noise DSLR camera, something like this, right? I mean, something that you probably have at home. Start with a short focal length. Even a camera lens, right? So I said 35 millimeters, or something in that order. Something that will give you a very large expanse of the sky, a big field of view, and take some pictures and see those pictures. Normally, what you would do with, for example, with this lens, right here, I can literally take this setup just like it is. There's no mount in here, right? I mean, we only have a little ball mount in here, but it doesn't track anything in the sky. But again, because we actually have a very large image scale, I can take like a 10 or 15 second image of the sky, and I don't need to track anything. And that will be a kind of an interesting picture. And take 20 or 30 of those, and then you can put them together, and you'll end up with a very interesting wide field type of image that you'll be surprised. You'll be surprised about how much stuff you actually can see and take and see it right away. It's just fantastic. It definitely will whet your appetite into astrophotography. And then baby steps. If you want to, you can actually start getting into a little bit longer focal lengths. And then you'll see that, oh, wait a minute, now I need something to actually track the objects in the sky. And I'll show you what I actually have for literally just going out the door and take a picture of something that I would like to take maybe like 5 or 10 minutes. And then start thinking about, because as you go with your baby steps, start thinking about your good tracking mount and getting into a little bit longer focal length telescopes or lenses is fine, okay? One thing that I'm not going to be able to touch here at all is the image processing software. This is imaging. It's only one side of the coin. There's two sides of this coin. One of them is the acquisition of the data, i.e. taking pictures, right? The other one is processing those pictures, okay? And that is one thing that we actually discuss a lot in CASs, right? How to use image processing software to take all the images that we have taken and then put them all together and have a nice picture. Full disclosure, I like PixInsight, and that's what I teach. So basically, that's all you're gonna get from me is instruction on PixInsight. It's a commercial image processing software. It was written by astronomers, and it was for astrophotography, and this is a long. When I say long, it's the learning curve is quite high because there's a lot of tools and everything that's all together. But when I teach it, I try to make it as what can I say, as procedural as possible. In other words, I'll give you some steps that you can actually follow, and you'll be able to get an image that you'll be happy to actually show to your better half or everybody that wants to see it and so forth. And the most important part of actually astrophotography, patience and perseverance. Okay. As I said, this can be an incredibly frustrating hobby. The results, when you're starting, sometimes the results are not what you were thinking about. But sometimes you'll be surprised. I mean, we actually it was you, right? I mean, we actually had one of our members, CAS's members, actually, he took one picture and it turned out to be beautiful. It's the first picture he ever took. It was amazing, right? So there you go, right? I mean, there is all kinds of surprises that are associated with this hobby. So you can actually get some interesting imaging results, right? Total lunar eclipse, right? 70 millimeter, just zoom lens with a with a DSLR, just with a T5i, okay? And we're talking about literally 4 or 5 seconds. And not too much of processing at all. This is, of course, yeah. You see the horse head right here, right? The flame, and then I don't know what that is over there, but it's somewhere in Orion. But anyway. This picture actually, this is, you'll be happy to know. I mean, this picture was taken with a DSLR. This was also with a 70 millimeter lens. This actually made the front and back cover of one of the astronomy magazines. Okay, they put it in half. They not cut it in half, but just doubled it, made it the front and back cover. That was quite an honor to be able to do that. Okay, this is a TB85. So this is 85 millimeter telescope, 660 millimeters in focal length, and with just a DSLR. And this is Pleiades, right? And it has, you know, I mean, there are better pictures of this everywhere, but this was easy. This was easy to take this picture, and relatively painless. Okay.
I found this on the web.
No, you didn't. City keeps trying to help me.
That's where your picture is.
Yeah. Hush. All right. So the same thing. This is a 85 millimeters DSLR. Okay. So I mean, think about this. I mean, I haven't used a astronomical camera in any of these pictures yet. Even this one, right? Andromeda. This is an early image of Andromeda. Okay. Again, 85 millimeters on a DSLR. So, I mean, for goodness sake. Now, okay. Time goes forward, and now we actually have a difference, right? So this is actually 3,000 millimeters, okay? So imagine, this is with a CDK. So this is a corrected Dalkirchen telescope. And in 2014, M82 had a nice supernova in there. And in 2014, I actually started working, collaborating with OSU, and they said, well, you know, yeah, we know that it's in there, but they would like to actually have a color image of the supernova. And I said, sure, no problem, okay? I'll be more than happy to do that. So basically, this is a monochrome camera. So this has red, green, and blue colors put all together, and you know, an order of magnitude difference as far as equipment that was used to actually make, you know, this image. This is also a, you know, Galaxy CDK, you know, 3,000 millimeter telescope with an astronomical camera. And, you know, I mean, you can take, again, beautiful images. It does, I mean, this is the stuff that I truly love to do, is to share what is out there with everyone, right? So kind of a little bit smaller view, if you will, zoom in of the, and by the way, it looks a lot better in this than over there. The helix, right? I mean, that's, this took 2 years to actually take this picture, folks. This is kind of an interesting story. You know, this is on the constellation of Aquarius. Aquarius doesn't actually raises too high in the Columbus sky, and we have trees in Huddville. So I was able to take in the order of about maybe 12 hours in 1 year. It wasn't enough. This is a very faint object. It's huge. This is as big as the moon, by the way. This is the size of the Helix Nebula. It's as big as the moon, but it's very, very, very faint, which is how we started. And so I had to wait 1 more year until it come back, go past the trees, and take a few more hours. And I was able to take enough data to be able to take that picture. This is, yeah, I know this one came with my name in the back here. This was real hard. But yes, for this one is hydrogen alpha. Yeah, actually this one has hydrogen alpha and sulfur. The sulfur is very faint, but it's actually in the outskirts. You can see a little bit in there. But yeah, hydrogen alpha and sulfur. The crescent actually has a lot of that. And, you know, regular nebula, the Trifid, right? And that's the last one, I promise. So, again, beautiful show that the cosmos actually provides to us. we can capture this. My joy is to share it. My joy is to basically kind of share what we can actually see and capture, and that is out there. But it's not only, right? It's not only pretty pictures, right? As Burnham actually said, astronomy also offers the privilege, not to be taken lightly, of adding something to the knowledge and understanding of man. Right? So you can do a lot with your telescope. Think about this. Professional astronomers, they're probably, there's not that many, right, around the world. And basically they rely on amateur astronomers who actually help them out on gathering, like astrometric research, things like variable star research, AFSO, the American Association of Variable Star Observers. They're very interested on any data that you actually take that has to do with variable stars. You can do exoplanet research. OSU actually has a group of folks that, grad students and so forth, that are actually doing exoplanet research. And they're eager to actually get data, right, if you can actually provide data to them and so forth. Supernova research, right? I mean, I had the privilege to actually work with, with OSU, basically Chris Stanek, to actually collaborate in Assassin, with astrometric follow-up, and literally discovery of supernova. You can also do the near Earth object research. So looking for that big nugget, the one that's coming, and we don't know where it's at, and so forth. So I know there's a big hammer. I've been reading something, they call it a big nugget. So NEO research, you can actually provide some data in that too. If you see something that is moving and you don't know where it's at and everything else, they'll be more than happy to actually know what the heck is it and calculate the orbit of it. And also comet research, with the last comet that we actually had, 2022 E3, a lot of people were kind of interested on it and took pictures, and the green comet, right, they call it, and so forth. So yeah, absolutely, and more comets are coming. So that you can actually help on that type of research. This is an eclipsing binary, a well-known eclipsing binary in Hercules, called SZ Hercules, and you can see how it actually the magnitude changes from 10.3 all the way to 11.3. So basically one magnitude change, and then as it eclipses, and then it goes, and these are reference stars. So you know that basically this change is true, if you will. AFSO, again, the American Association for Variable Star, they love this kind of stuff, and you can send it to them, and they'll be more happy to take that data and add it to their archives. Much harder to be, right? To do is exoplanet, and again, I'll point to the difference in, right? I mean, you can nearly see this with the naked eye. If you get very used to actually seeing stars, you can actually do variable star research with the naked eye, but not exoplanet. Exoplanet is millimags. The difference between this planet actually eclipsing a star goes from 11.54 to 11.56. So this is actually relative magnitude change for this exoplanet in here. It's kind of funny because to do this you need one clear night. 4 or 5 hours. 1, 2, 3, 4. 4 or 5 hours of actually be able to do this, and no high clouds, no wind, very, very, very rare conditions, observing conditions for Ohio. So I did 2 of these. I did this one, TRES 2, and then another one, which I don't have here. But and having done that, I realized that I'm going to retire because everything else I'm not going to be able to, everything else is going to be a 0. But it can be done, and it can be done in Ohio. I mean, amazingly enough. So I talked a little bit about Assassin, and just to give you a quick summary of what it is. Ohio State University project. Chris is the one that actually started this in 2014, and they have telescopes in South Africa, Chile, Texas, and Hawaii, and they take a picture of the whole sky, the whole night sky, every night. So northern hemisphere, lower hemisphere one night, and then the next night the same thing, northern and southern hemisphere. And then they subtract. I mean, they do literally just a simple subtraction, one from the other, and what ends up being is just basically just a black map with just little points, and those points are transients. They call them transients because there was a change from one night to the next, right? Now, it's a whole sky, so it's a huge, huge, composite of the sky. The Achilles heel is that the resolution is very, 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 very bad. It's 7 arc seconds per pixel. And remember, things are moving at 15. But anyway, so 7 arc seconds per pixel is not enough to actually know what it is. They only know that there was a change, right? They have a pixel that didn't have any data or any energy in there. And then the next night, there was a pixel with energy on it, but they don't know what it is. So the call went out, actually, he actually made a presentation here in 2014. And he said, hey, can somebody is willing to help me, to actually find out what these transients are? Yeah, I can do that. My telescope, my CDK 17, my 17-inch telescope, my resolution is 0.6 arc seconds per pixel. And, it's like, yeah, absolutely. I mean, if it's, if it's convenient, I'll be more than happy to, to actually do this. The system is it's automated in the sense that once it finds a transient, it sends out an email that says, I don't know what it is, but there's a spot in the sky. Here's the RA and the right ascension and declination. And it has a little bit more data, basically nearby galaxies and stuff like that. And then if you want to, you can go on and look at it. Well, in 2016, I started in 2014, I'll show you later, but in 2016, this happened, right? I mean, here's an image, an archival DSS image, and you can see this galaxy in here, and there's nothing there, and here's the same galaxy, right here, and there is a supernova, right? Now, it's kind of funny, because when we were doing this, there were like 6 people actually working with Chris, and one in France. We have one in Australia who takes all the southern, objects. He's a funny guy, and then they had like a couple more people and myself, and it's funny how competitive these things sometimes are. Okay. So I took this picture, I took that picture, right? I mean, this one right here. I send it out, and basically 3 minutes later, somebody else, actually it was the guy from France, actually also sent out the picture, and there was this conversation about who's going to get the honor of actually of the discovery, and well, you actually get this, a discovery certificate, and there is yours truly. So there you go. Primacombe is the guy from Australia. Real nice guy. But there's Chris Stanek, so and the assassin team all together. So I mean that's pretty neat. I mean what is really exciting about this is that when you actually take this image and you see it on your monitor, right? This is 500 million light years away. And you, the human, are the first one to actually see this, right? That is amazing. I mean, that really touches you. I mean, it's really exciting, and it's really touches you. It's really quite neat. And to be able to, get a little bit of recognition, right? I mean, with things like this, from the IAU and so forth, is neat. But to be there, right? I mean, to actually do that, and then to be able to do that, bunches, more, and then some more. Basically, it's amazing, right? I mean, and currently, there's close to 30 supernova discoveries under my name, which I'm very proud of, and so forth. One of the things that also happens is that as part of the collaboration and work that the group, this is not me alone, right? I mean, the group has actually done for Assassin, you get to be a co-author. So you basically get to be mentioned in, in publications that are, peer-reviewed and everything else. And this was on 2017, number 4. 4 weeks ago, we published, and really, I'm very happy to say that we published number 5 for the, the last of 20. It actually ended up in 2020. That's where we actually ended up that one. So this is important, right? I mean, again, what other hobby actually gives you the opportunity to actually provide something, to add something to the body of knowledge of man, to have the privilege to be able to do that and so forth, and you start, very modestly. Okay, we're not talking here about you take the time and you take you do your work and so forth, but altogether it is in my mind quite a privilege to be able to do this. This is why I love to do this, and again I thank you for giving me the opportunity of sharing this with you all. Appreciate it. Questions? And if you want to see some equipment, I brought something here to actually show you. Thank you. Again, this is a very rigid tripod, but you only need a tripod, right? We were talking about, what you need for taking like 35 millimeter images and so forth. You only need. You basically only need a mount that you can take a picture of in here, because again you can take images without having to do any tracking. Okay, so let's say that you want to actually do let's say a couple of minute type of images. Then I'll show you how easy, if you will, is to actually do this. In a few minutes, you can take your equipment, maybe, come on. I just don't want to actually get my camera. There we go. So you take another gizmo. Right? I mean, this is like by Manfrotto, but basically what this does, it allows you to put this at make this a equatorial type of mount. Okay? remember I told you about the fancy, oop, there we go. Okay. You can use it in the northern hemisphere or southern hemisphere. And basically what this does is, remember that there was an arm that actually moved and so forth? This arm actually moves back and forth. And you take this baby right here, you put it here, and now you have a system that actually will follow any object in the sky that you're willing to, that you want to take an image of. Okay? There you go. You do need batteries for that, though. So the good thing is that you don't need a huge amount of batteries. You need something like this. And this will actually, this will actually last all night. I mean, this is basically 8 AA batteries. This will last all night.
Is that the rig you took when you went to like Australia?
Yes, exactly right.
Packed it on board the plane, yeah.
Yep, this was basically all that I ended up taking with me to take images. Basically my imaging rig when I went to Australia, and I carried that package, that backpack. This is a very light type of tripod, also attached to that to that in there, and it has a place for the computer, for a regular small laptop, and that was it. I mean.
And what do you do to polar line with your polar procedure?
Woo! That's pretty good. Great question. This thing, I don't know if you can actually see it from there, but I'll move it over. So that's ready to start. Basically, when you press that button, and it has like a small green light that actually pulsates in there, that's tracking. That's actually moving at sidereal rate. And this long, this arm actually moves along this long screw, and it gives you about 2.5 hours of tracking in there. So let me show you the polar alignment. There's a polar alignment scope, and because this is actually, you basically just put it here, and it has a what do you call that? Magnets. It's magnetic, and you basically look through here. You polar align it, and once it's polar aligned, you can take it off, and you're done. And it again because you're not using this with a 3,000 millimeter telescope, right? I mean the largest, the longest. That I had, not even telescope, but the longest lens that I actually have is 400 millimeters, which is significant, but it allows you to take some nice, some decent images altogether. And once it tracks, once it's polar aligned correctly, right? I mean, a good polar alignment, it's kind of very for the weight, the performance is actually quite amazing. Yes, sir.
How hard was it in the southern hemisphere to polar align?
Oh yeah, I have stories about that. Now this one, actually, it's an interesting thing, right? Because everything is backwards. You see, it has a north and it has a southern. So for the southern hemisphere, this they didn't like it, but this arm was actually just facing this way, and then it actually kind of follows, the pole, the rotation of the Earth in that way. So yeah, I mean that's really again This is, we're not talking about a ton of money in here. It's some money, but it actually is something that is transportable. Oh, actually, I'm trying to remember, did I take this to the 2017? I may have taken this same setup for the 2017 solar eclipse. Because I don't think I was following the sun. So I think I actually took this same thing, this same setup for the 2017. Yes, sir.
Have you used that with, say, at 200 or 300 millimeter focal length?
I have used it at 200 for sure. I haven't used it at 400.
Okay, 200, okay. So that's interesting because, many years ago you couldn't have done this, but we've talked about this recently among ourselves. With the modern, latest generation DSLR or mirrorless cameras, or with a lot of the one-shot color cameras, the CMOS, which are basically the same sensors, you get such a low noise that you can take a lot of short exposures and get a good image. So a mount like that, that's not going to compare to that $3,500 Losity that he showed you in the picture before with a long lens. But if you can shoot at 200 millimeters and maybe just get 10-second images and take a bunch of them,
Yes.
and put them together, nowadays you can get some quite outstanding pictures. And 200 or 300 millimeters is fine for a lot of deep space objects like the Rosette or M31 or any number of other things. So you can actually do deep space with that rig if it'll work.
Mm-hmm. Yeah.
With 200 or 300 millimeter
Most of
lens.
us that have a camera have a telephoto lens, and you
Right.
can use it to shoot animals at the zoo.
Yeah.
So.
But that brings the cost of the whole system way down to
Way
get
down.
started. And there's a lot of deep space things that you can take. I mean, Isaac was talking about deep space, you need a long focal length. Well, you do for shooting a lot of small galaxies and stuff.
Yeah.
But there's a dozen or more big objects out there or more that you can shoot at 200 or 300 millimeters.
Absolutely.
Yeah.
Absolutely. But and again, I mean, it's a matter of just, if you have the lenses already, I mean, that actually helps. But, you can literally just, oops, sorry. Wrong.
Did you take that first picture of the horse head with that camera there, with that setup?
Yeah. One of the pictures of the horse head.
The first with this very small picture of the horse
Yes,
head.
with this camera.
No,
With this
when
camera.
the
But it
one
was
with
the,
just the horse head where it was in close up.
no, the long one. The one that has the horse head and
And
42.
riding them and all that. Did you
Yes.
take that with that camera?
Yes.
Or that setup that you just took down?
I think I actually. Yes, actually I did. But that was in Hudson and I was using a camera. So, so you can actually have something like this and it'll handle it, right? I mean, as long as it's.
But I mean, the CMOS cameras that he was talking about, the CCD and CMOS, are excellent because they're cooled and they have a lot of nice features. But a modern DSLR or one-shot color camera basically use the same sensors. So they become one-shot color cameras, and you can, any of those pictures that he took up there, you could have done with a modern DSLR or CMOS camera if you have the right mount and the right optics.
Correct. That is correct.
If you want a really inexpensive, it doesn't work so well with long lenses, but if you're taking wide field, you can get like an older iOptron mounts that is for about $200.
Ioptron Sky Tracker.
Yeah, Sky Tracker.
I've seen
Yeah.
those.
And,
They're like $200.
If you're for wide angle, you can get some good. Good.
I shot for 5 years on that exact mount.
Yeah.
And
And just step up from that.
Yeah.
Yeah, it's correct, exactly right. One of the things that is kind of neat is that as Tom actually mentioned, with the modern cameras, I mean, you actually have the ability to be able to take a ton of pictures, short durations. Then, the software put it all together. I mean, it's just basically, it's no big deal. Nowadays, the cameras will be able to do that, and the software will help you in actually doing that. So, well, any other questions?
Yes, ma'am.
This is probably like maybe too basic for me.
No.
I'm looking to buy my first telescope soon.
Yes.
So it sounds like from what you said that a refractor is probably the best one to start with.
I'm gonna say that you need a pair of binoculars first.
The what?
A pair of binoculars first.
Oh.
I want to start you with a pair of binoculars first.
Okay.
Talk to me at the end, or let anyone that may be here.
Okay.
They'll probably lead you that way. Because I mean, that actually makes you'll be surprised how much you actually see, and you'll be surprised how quickly you learn the sky. It's actually very, very useful. So that's what I recommend to begin with, and we can talk about it once we're done.
And even after you buy then the telescope, you'll still need the binoculars.
Yeah.
So it's kind of, you
You-
don't graduate from binoculars to telescope, it's, you get both.
You'll keep it.
Binoculars first,
Yeah, you will keep them. You'll keep them.
Okay, cool.
Yeah.
In fact, my class next month is going to be binocular astronomy, and I'm using them to augment your observation.
There you go. Excellent. Any other questions? Well, thank you very much, everyone. I appreciate it.